Appreciate you taking the time at the last minute to fit this change into your schedule. We had a lot of folks that were interested in this talk the first time, so I'm excited to be able to share with you what they saw, and hopefully you take away from it the same value that they did. This is a talk about how to extract the maximum amount of performance from a combination of EC2 and AWS. Wait one more minute. All right, everybody, check your email. Now stop, and we can collaborate and listen. So maybe to start this thing, probably the easiest way to describe what we're going to talk about today is the fact that the Elastic Block Store service, in no part of those three words, which are interesting, does it say disks, or solid-state disks, or flash drives, or 0-in-1 AutoMagic devices powered by hamsters, or anything weird like that. The Elastic Block Store is a service, a RESTful web service for us that allows you to provision storage that connects to the EC2 backplane. That service exposes a set of behaviors, and those behaviors are different than the behaviors of physical devices. So a lot of what we're going to talk about today are the mechanics of that difference. Most of the folks that I talk to that work in storage, we've gotten really good at understanding the behavior of the physical devices that we've been using for many, many years to store data. And in a lot of ways, those can give you some bad preconceived notions. Hopefully today disabuses you of some bad assumptions about the way storage should be used in AWS and gives you some new baselines and new tools to establish the highest performance patterns for deployment across a pretty broad range of workloads. So if storage has changed, if we've done a lot to change the way that storage behaves, what hasn't changed is the workloads you're trying to run storage on. So there are a lot of folks running relational databases on AWS, not the least of which includes our managed service, which consumes the same resources you have access to. Our NoSQL databases across all sorts of open and closed source application layers all consume storage at an incredible rate. Data warehouses, file sharing, file stores, media systems, all of those require access to a file system rather than an object store, and as a result, need to be implemented on some kind of block storage service. We have one of those, and we're going to talk through the mechanics of making your workload work fastest on AWS. So, I am willing to bet, given the fact that you paid $1,300 to sit in this chair, or if you are the winner of the Cloud OSS prize, how about no dollars, that you know the definitions of these things. But to set a level, to set a basis, I/O operations are the individual transits of data to and from a storage device. We measure those typically in the number of them we can get done per second, hence IOPS. Throughput is the total aggregate of the data we've moved. Since each I/O can happen at a different size, we also want to be able to measure the megabytes per second or gigabytes per second of throughput that we can deliver. That throughput happens over some kind of connection, and so since the connection exists, there's an amount of latency, the delay between when you've asked for a piece of data and you get it, or when you write a piece of data and get a response that it's been written. We measure storage and capacity typically in gigabytes, and a lot of the talk today will be mostly around the first three and this bottom one, block size. How do different applications interact with our storage backend at different average block sizes, and how can you optimize implementations to take advantage of that? So the interesting bit, you can also order hard drives from Amazon. They just don't come by way of a REST interface. And if you look at the back of the box, you get all of these physical characteristics, mechanical characteristics. There are this many spindles. And inside of those spindles, there is this head sector density. And the areal density constructs a net number of gigabytes. And there's a rotational rate of the drive media and all of these numbers. Many of them you have likely done the calculus on to compute the number of, say, IOPS, or the number of megabytes a second for sequential reads, or other things that you can expect from this device. That skill's one of those things that differentiates the folks that have the crappy slow databases versus the super awesome fast ones. Conveniently, Amazon has the ability to do that math as well, and has built services that make it so that you don't have to. The block storage services from Amazon generate those values directly and can be provisioned by you to an exact speed. So provisioned IOPS allows you to provision anywhere from 10 to 4,000 IOPS per EBS volume. And you can do that at a ratio of all the way from a terabyte at 4,000 IOPS or a terabyte at 10 IOPS if you really don't want to move the data back and forth, down to a minimum ratio of 1 to 30, which gets you to around 134 gigabytes for the 4,000 IOPS volume. That'd be the smallest possible size. That lines up kind of interestingly with those old 15,000 RPM disks. We thought that was a pretty good number. So because you have the ability to dial exactly the number of IOPS that you need for a given workload, you aren't limited to the building block of physical devices. Once you buy a hard drive, say it can do 200 IOPS. If you want to do 202, you need 2 hard drives. With provision IOPS, you just change the number from 200 to 202, and you're off to the races. Constructing these happens by way of our CLI, our RESTful interfaces, our online user interfaces, and potentially third-party applications that you have that sit on top of us. Provision IOPS is one system from us. There's also another, the original EBS, called EBS Standard. EBS Standard and EBS Provisioned IOPS are substantially different infrastructures. They're not built the same way. They have different software. We wrestled with the concept of even calling provisioned IOPS a different product from standard EBS. So recognize that even if you did an amazing amount of testing on the behavior of standard EBS, that doesn't have anything to do with the behavior of provisioned IOPS EBS in the same way that the performance of your RAM is different than the performance of your network. So how does standard EBS work? Standard EBS provides 100 IOPS steady state with best effort bursts to low, like 1,000, 1,020, 1,100, 1,400, maybe 700. All of that happens on a best effort basis and is not something that you provision or configure. And as a result, there's a pretty significant amount of variability of that performance. You'll also observe behaviors where short-term bursts of work are accepted by the standard EBS system pretty well. But then steady state workloads will return to this wall rate of about 100 IOPS on a steady state basis. EBS does have, as a result of that, a variable throughput. Just because you can move an I/O to a disk doesn't mean necessarily that you can move every bit, but in general, standard EBS moves and is capable of slightly higher throughputs per I/O than provisioned IOPS, and we'll go into what that means in a second. Latencies for EBS standard range in the sort of 20 millisecond range for reads, with writes faster than that, and that's kind of an interesting detail, somewhere in the range of 10 milliseconds. But again, latency and total IOPS throughput are best effort on EBS. Contrast that with provisioned IOPS. So with provisioned IOPS, you get within 10% of what you provision up to 4,000 IOPS, 99.9% of a given year as provisioned. So that means for a couple of minutes out of the year, you might see it go down below 3,600 or so. If it goes to 3,400 or something, that's a ticket you file to us and say, this one's messed up, you guys are doing a bad job. Throughput on provisioned IOPS happens in 16K blocks, and that's a really important number. As a service rather than a physical device, that's a throttle. That's a system that we've used to constrain the performance that you receive. That also allows us to maintain the consistency that you see. So different than a physical device that isn't operating in a throttled, managed way, this device will deliver what you provision in an incredibly consistent way. So you also have a requirement around queue depth. So we'll talk a lot about queue depth and how that works. With standard provision IOPS EBS, you'll see latencies that are much, much lower than standard EBS. Easy rule of thumb is that starts in the range of the number of IOPS you've provisioned, take a second and divide it by that. So if you have a 1,000 IOP volume, that'd be in the millisecond range. If you have a 4,000 IOP volume, you could be as low as quarter milliseconds, which is pretty spectacular. So the general thing that you'll take away from this, you're going to hear me say a lot about these two products. Please use provisioned IOPS and EBS Optimized for your databases. Standard EBS was not designed for those workloads. Standard EBS is a root volume service designed to allow EC2 to start and stop instances. And so the characteristics, the behavior of that disk, they all line up with what you'd need for a good instance booting service. You'd like the ability to do bursts of writes like you'd do to swap memory on a VM. You want to be able to provision it rapidly, and you want low cost because typically the root volume on your average computer doesn't get worked that hard very often. Now, provisioned IOPS is built different. It's built specifically to be worked as hard as possible for years on end at maximum throughput. So we'll talk through why those two are so different. So you also might have noticed, I'll go back a couple, there are asterisks on this slide, and I don't like those any more than you like the little asterisks on how much sugar is in your cereal or how fast it is that you're going to burn through your network bandwidth on your mobile phone. So the asterisks are for a reason. Let's think about the building blocks that are a part of the system that makes up the ability to store writes. So you have an EC2 instance, you have the network connection between the EC2 instance and the storage service, and you have the individual IOPS that make up that connection. So you can think of, at any given speed, that there's a certain finite number of slots. So say you had a provisioned IOP volume provisioned at 10 IOPS. That means you have 10 opportunities to do work. If you don't take one of those opportunities, you lose it. We don't give them back to you. It's not a bursty service. We meter at a very fine grain. So what happens when you write a big I/O, a 32K or a 64K I/O? That consumes multiple of your opportunities to write to storage. It consumes more throughput over the network. And so if you run out of bandwidth on your connection, you may see throttled writes independent of the provisioned IOPS or standard EBS's ability to take those writes. And we'll talk through the mechanics for that. You might also write much smaller IOs than that. If you're on an Oracle database configured at 2K writes, or you're on a MongoDB database that's got 4K writes for small operations, you don't get any bonus additional magic random IOs. Where you provision 4,000, you get 4,000 out of the device. That's the way that it works. Even if you don't fill each of those opportunities to do work, that's not something that we give as extra. So you also have this concept of queue depth. If you don't have enough work in the queue of work to storage, and you miss one of those opportunities to write to disk, we don't give it back to you. So you need to maintain enough queue depth to keep the storage interface loaded. You also can't overload the queue depth. If you have so many writes waiting in line, you can cause latency that exceeds basic buffers at the operating system tier or the networking tier, and as a result, non-linearly increase latency. That's a problem. We'll talk about what that looks like. So how to go faster? How do we make this better? So let's say if you just add more provisioned IOPS when you're already saturating the network connection or saturating the performance of the EC2 instance, more volumes won't help. It doesn't make it go any faster. You can hook up 500 provisioned IOPS volumes at 1,000 IOPS apiece to an M1 small, and by gum, you'll not get much more done. You also could not have enough provisioned IOPS for a given workload, right? So it is possible for the storage subsystem to be limiting your total throughput capacity. And if it's under-provisioned, you'll see a bloom of queue depth, and as a result, an increase in the latency of each of your individual writes. You also could radically over-provision the EC2 side in comparison to the provision IOPS side and not see any benefit. You get this big honking machine, and you've got a 7 IOPS volume, not going to get a lot of work done. So what's the right thing for any given workload is to make the combination of these 3 resources combined in a uniform, efficient style. A way to think about this is you take the motor from a Honda Civic and you put it in a diesel train, and you take the motor from a diesel train and you put it in a Honda Civic. Neither of those vehicles is going anywhere quickly. You really want the right parts in the right places. So building patterns of infrastructure that are balanced. is the way to efficiently extract value from our systems and have oh yeahs with your asterisks. So architecting for performance, how do you know what balanced looks like? So we haven't published this stuff yet. This is brand new, so welcome to one of those benefits of the $1,300. We are working on formalized publication of the exact performance throughput to EBS for every instance type. This is a preview of that guidance. So we are now showing a couple of interesting things. One, the relatively low amount of network bandwidth that exists between small size instances and the EBS system gives you a better guidance as to what the right expectation is. We're also showing, and it's a place that I really want you to squint and look, at how much faster the cluster instances are than everything else. So that's CC2, CC1, CG1, the new I2s, the high 1.4XLs, the HS1, 8XLs. All of those instances are on the cluster compute network, 10 gigabit, full bisection, non-blocking, zero oversubscription, monster network is what we call it sometimes. And that is not linear in relationship to cost. So if an M2 4XL is $1 something an hour and a CC2 8XL is less than $1 something an hour, if it's maybe twice as expensive, it's roughly 8 times faster to disk. So if you're able to consume these larger instance types, you're able to get pretty nonlinear benefits around storage performance. And all of the numbers on the left are built around the assumption that your application is writing 16K blocks. So if you're writing smaller block operations, you can drive larger IOP counts. We'll talk about the mechanics for that. So places where that guidance starts to look funny is when you don't have EBS optimized. So the EBS optimized provides a totally different network fabric for interaction with storage. So the red line at the bottom where it says with network load test, that's us writing 200 megabits a second of really awful random traffic over network to this instance. The no network load is no network load. So if you run this workload on EBS optimized, you see totally linear performance. Because we have a separate network channel to EBS, there isn't contention between the network operations to the internet, to other instances for replication, to other AWS services, and your interaction with EBS. If you run this same test without that little checkbox, I can tell you the numbers are worse, and they're kind of catastrophically worse. It's really important if you intend to fully utilize any use of provisioned IOPS that you have EBS optimized turned on. In fact, if you go and look at Trusted Advisor, a couple of days ago, we added a check. And that check says you have provisioned IOPS volumes, and they're hooked up to instances that do not have EBS optimized turned on. We don't invent a check like that if there aren't thousands of customers making that mistake. And they are. Hopefully you aren't. And hopefully after this talk you won't. But I can tell you it's getting done a lot. Now, that benefit, the EBS optimized improved channel to the storage subsystem for EBS, that works both for provisioned IOPS and for standard EBS. If you need non-contention between network traffic with the storage subsystem, EBS optimized works for both storage types. So we have a lot of folks that are trying to get to higher throughputs, but don't need the consistency guarantees around provisioned IOPS that are using that with standard EBS. Pretty powerful pattern. So provisioned IOPS, again, is optimized for your database workloads. And it does provide, because of its throttled, you can say computer-generated behavior, a very different experience from many of the physical devices that maybe you're used to using. It has the same performance for random and sequential workloads. We don't care. Your physical devices don't do that. We have 16K blocks as the measure. All sorts of different disks come in different block optimized sizes. As you move into solid state hardware, you have all kinds of different types that are the right size. 16K is actually relatively large for your average SSD, and there are some complexities around databases that use large block sizes to take the best advantage of SSD. Provision IOPS resolves that. So some places where things might look odd. Let's say, for example, you use an M1 large. So if you go back to that earlier chart, M1 large has somewhere on the order of theoretical max 64 megabits a second connectivity to the storage subsystem. If you use provisioned IOPS, that's the number that you get. So if you hook up a 4,000 IOP volume, and you do a little calculus in your head, 4,000 IOPS times 16K is 64 megabytes a second. So they're exactly the same speed in the sort of theoretical level. So if you have any loss of a single bit in any of those transits, if there's any latency gap or variation, even at 0.1%, you start to lose opportunities to write to storage. So at 4K operations on an M1 large, you see the full 4,000 IOPS, maybe even slightly above that from what's provisioned. But at 16K blocks, you're right at the absolute threshold of what's configured. And so you'll tend to see just slightly less than what you asked for. That's not provision IOPS doing what it's not supposed to do. You've actually saturated the network channel. If you take that same disk and connect it to an M3 extra large, it goes up to the 50 or 4157 that you'd expect. Also, interestingly, if you look at the sequential 4K operations on the instances with higher bandwidth, if your operating system can serialize random events through the file system into the same write operation to storage, you may see from your instances or from your software's perspective a higher actual number of IOPS. Right? So your computer thinks you're getting 6,000 done, where since we're only metering at 16K, we think you've only gotten 4,000 done. If you compare that number to what's happening in CloudWatch, CloudWatch will say 4,000. Same example, only even more exacerbated on the M32XL, which has double the bandwidth. Now you can move even more of these sequential 4K operations to storage. With random, you don't get that benefit. Each of those operations is going to a different target. As a result, the operating system won't consume those into, or serialize them into single writes, and so you don't get a bloom of performance there. So another place to look is at the larger block operations. You're going to run a data warehouse. And so you don't even really care about IOPS at all. You want to know about the megabytes a second of throughput. Provisioned IOPS is just as consistent at delivering megabytes per second as it is at delivering IOs, because in this system, they're effectively the same thing. And you'll see the same average bandwidth throughput, the total number of megabytes a second, across different block size operations. But wow, the IOPS will look really scary. Why is this system only doing 116 IOPS? Well, it's because you're writing many IOs per block write at 512K. The larger, higher throughput instances allow you to get to the full maximum for each EBS volume type. So another hugely important set of metrics are around the latency behavior of these devices. So this goes back to the queue depth that we talked about. There is a totally linear relationship between the queue depth that you're able to drive and its impact on latency. Or, linear isn't the right word, but there's a connection there that's important to understand. So for write latency, you need a relatively low queue depth. When we originally launched provisioned IOPS, as we measured against the workloads we were testing, we saw slightly different behavior than this. And so we've retested and retested across a broader range of customer workloads. And at the 4 to 8 queue depth mark for 16K random writes on a full throughput EC2 instance, you can see in the low single-digit millisecond latencies, 1.47 per operation, 2.03 per operation. You'll note at short queue depths, latency goes up, and at long queue depths, latency goes up. So for write workloads, the original guidance isn't accurate. You want to be more in the range of 1 to 500 or 1 to 1,000 in order to optimize on the write side. And on the read side, you'll see a different behavior. So just like lots of different services, there's a little nonlinearity there. You'd want to optimize for a higher queue depth on reads, and you'd still be able to earn these low single-digit latencies. You'll also know a much bigger jump. The scales on these two charts aren't the same. So on this chart, you're stair-stepping upwards by single-digit milliseconds. At the top, you're at 7.7 milliseconds latency per operation. On the read side, that's 90 at the top. So it's really crucial to not drive an overwhelming read load against the provisioned IOPS system. It's not designed to do that. So that guidance starts to look more like a queue depth of 1 for every 200, which is pretty close, or 250, which is pretty close to our original guidance. It gives you a little more room there. So from a design standpoint, your application may have different requirements, may be deeply bounded by latency. A way to think about that is, is the event that happens in your database or your data store directly in the line of an event that is touched by a customer or a user? Probably the most extreme examples of this stuff are the events that happen inside of the ad retargeting efforts at sub 100 milliseconds full end-to-end round trip. But there are lots of other places where reducing the latency of operations makes better user experiences. So if you're doing analytics workloads or big OLAP tables or you're grinding through chunks of data, latency may not matter to you very much at all. So you may want to tune this value in order to be able to extract the performance value that you want. And generally, very, very high queue depths. We're already looking at many customers starting to implement alarms in and against CloudWatch at extreme queue depth heights as an indication that something's gone wrong and that they're going to really want to adjust the behavior of their application. So another question we get quite a lot from a performance standpoint is the pre-warming of EBS volumes. There is a lazy load process and a lazy assignment process from the EBS subsystem to the storage that you consume. That process is the same for brand new, net new EBS volumes as it is for volumes reconstructed from S3 snapshots. You'll see typically a 5% or so impact, extreme worst cases in the 50% range. We have customers that have experienced numbers much higher than this, really, really terrible performance in the 80% range. Those are indications that something has gone wrong and you should be communicating with support. These are values for the correct real behavior of the service. When you access each chunk of data in an EBS volume, you warm or assign or provision that chunk of disk. And so for almost all of the customers that we've worked with, if they're actually intending to really use hard drives, there isn't anything they have to do. They just start using them and they work how they're supposed to work after a little bit. There's kind of this warming up period in the first couple of hours. If you're doing a synthetic benchmark, that's not the deal. You need to know how fast it's going to go, so you have to drive work across the disk to get us to give it all to you. So in Linux, that's DD. For Windows folks, there's a hilarious DD port called Chrysome DD. Give that a crack. Or I've even seen folks run Cygwin and then run DD, which is gross. If you have the time, you can do an NTFS full format that has the same effect. It can take a long time to pre-warm standard EBS volumes. Their IOP rate is very low, they're very big. You're gonna see that take non-trivial hours, typically in the low just above a day. For provision IOPS, you'll see that go much more quickly, especially if you are touching across the 4 megabyte boundary on blocks. So RAID, we have lots of questions about RAID. RAID is a useful tool. If your application, if your workload, like SQL Server from Microsoft as an example, has the ability to directly manage storage disks and storage volumes and storage pools, it's typical that your application does a better job of this than a RAID system would. You should just give your software disk, or EBS volumes in this case. If your application can't do that, RAID's the way to go. RAID allows you to aggregate the performance of multiple EBS volumes to deliver whatever IOPS number you need to get to for a given workload, given the constraints of the performance of the EC2 instance and the network connection. A pretty important piece of guidance, RAID 5 and RAID 6 are, and I cannot say this strongly enough, not recommended on AWS. Please do not do that. I'll explain why. So let's take 4 EBS volumes. And you want to write to each one, and you've provisioned, for the sake of this example, 1 I/O per second on each of those volumes. If you're going to write data, and it's at the block size of an individual disk, even in RAID 5, that only goes to 1 disk. That's great. It only consumes 1 I/O. Except you have to write parity data to every other disk. So every write costs 4 I/Os instead of 1 I/O, and it contends with the other potentially concurrent writes, increasing latency to each of those writes. So RAID 0, RAID 1, in extreme cases RAID 10, make total sense. Now, standard EBS and provisioned IOPS EBS both use and operate at much higher durability than a standard physical disk. The AFR for a provision IOPS EBS and standard EBS volume are both at 0.1 to 0.4% per year. That crushes and maims standard disk at roughly 4% a year. That's from our instance volumes. So if the folks out there who are thinking about super high performance systems on lots and lots of big SSDs, trust me, failure is a thing that you have to come to accommodate. You should listen to Werner. He's not joking when he says everything will fail at some point. And so those higher failure or lower failure rates on the managed system of provision IOPS EBS can make RAID 10 feel more like RAID 110, right? It's kind of already mirrored, and you're kind of getting mirroring on top of that. We have folks that do LVM direct to the disk. There isn't any problem with that. There's maybe more users that are using MD-ADM. We have a lower volume of support requests on that side. We have plenty of users that use MD-ADM to manage the storage and LVM above that to manage the volume you construct above that storage. So for MongoDB, for example, you'd create one big RAID so that any one of the logical storage volumes you construct can use the IOPS you have available. This is a better pattern typically. So, I can tell you about it on this slide anyway. So when rated and when using block sizes that are in the right range, on the larger instance types, you can drive truly ludicrous read performance in the not tens of thousands, but 50,000 plus range. Here, this test, we're showing 48,250. When you do RAID, probably the hardest single management change is the fact that because it's possible to have a write that's happening to multiple different EBS volumes happening at slightly different latencies, taking a snapshot from those volumes has to be done in a way that's more consistent, which means that the file system cannot be in a state of change when a snapshot's taken. For a standalone volume, you really can, in almost all cases, just smash the snapshot button and good things happen. So Storage 402, which was presented yesterday, so you're out of luck. You're just going to have to download the slides as they come public. But there are lots of new tools being released by folks on my team that will add new functional behavior around snapshots. Two different things that happen there. One, makes it much easier to manage snapshots of rated disks, and two, manages the snapshot diaspora as you take snapshots every 5 minutes on critical volumes. So it helps you clean up unused snapshot IDs as you age them out. Cool stuff. So we also think that it makes a lot more sense to not just give you the raw building blocks and make you do the calculus. We want to be able to publish just the straight cheat sheet. You run this software, you want to go as fast as you can go for each of the different 3 instance types that we generally recommend, or instance levels, something at 500 megabits, something at 1,000 megabits, something on the cluster network. We're just going to lay it all out, right? This is what you should be running. This works for, say, 80 to 90% of the cases that we see in each of these different workloads. And we're working really hard. This is another one of those benefits of reInvent. We're working hard to get this published, but we just don't have it done yet. So first, on the RDBMS side, you'll see the pretty significant variability in block sizes. And so you've got very different disk configurations that are the result of that, from all the way up to 24 provisioned IOPS volumes for your postgres SQL, which maybe you won't ever have to do again since we just turned it into RDS. Yes. Or down at the NoSQL sort of level, you've got some at the very, very small block sizes, 4K and things like that. Also for NoSQL systems, MongoDB, Cassandra, Couchbase, we'll be adding Aerospike and MarkLogic and several others to the list as quickly as we can. Similar behaviors, a couple of them do more to serialize I/O. So the MongoDB stuff, you will see that the actual storage system is doing 4Ks, but because the writes are typically so serializable that actual averages are more like 40K or 50K for lots of the synthetic workloads. So it's really important in Mongo to evaluate what we are actually doing with the database, because that has a much bigger impact in the average size than maybe other database systems experience. But generally, these are good starting points. Also the same for data warehouses and distributed network file systems. So file systems with typically much larger block sizes, you'll be seeing smaller numbers of provisioned IOPS, in order to get to the same throughput totals. And also the sort of switch typically here to sequential writes. So if that's this sort of cheat sheet, an important sort of number to hold in your head is, those are the throughputs that are the absolute maximums for each of those instance types as they interact with the storage subsystem. Now, those cluster instances, you'll note you can't poke that little EBS Optimized button. You get questions about that. You can't poke it because all of the work that we can do to optimize the channel to EBS has already been done, but that does not construct the isolation that EBS Optimized provides. So it is possible for you to write at that 50,000 IOP rate, and have that consume and contend with the network workload to other instances. Now we're talking about, lots and lots and lots and lots and lots of the megabytes a second. So it's more important to be careful with those instance types as you plan what the real world throughput will be for a replicated, say for example, data store, or for a data store that communicates much more heavily with the internet or other AWS services. So that's a little different than the EBS Optimized for standard instance classes. We also get lots of questions about the behavior of those systems in the context of the instances that do have high performance local storage. Hi14XL, the brand new super awesome i2 instances. Hope everybody's excited about those. And the HS ones, the big storage boats with 48 terabytes of local disk. So we see in lots and lots of patterns where you can implement replication. This is typically on the NoSQL side, but relational databases in some cases allow you to follow these patterns. Having SSDs as the primary write target, primary read targets in some cases, is an efficient implementation. But in a clustered setup, you're going to want at least one of those instances on provisioned IOPS EBS. The reason is that you can snapshot it. Getting that data into S3, where it is not 0.1 to 0.4% AFR, but 11 nines durable, some zillion number of trillion objects, and we haven't really ever lost one of those things, is a huge improvement in the durability of your data for business. If you have data and you like it and it's not in S3, I think you're a little weird. Right? So the process here of building a replication is dependent on the software. So some software can do this, some software can't. It's important that you test that for the specific workload that you've got. And there's also some tuning and behaviors, stuff that we don't have time in this talk to go into around the behavior of the local disks. A lot of it's not really a matter of time. The I2 guidance just hasn't been released yet. We'll get that stuff out as quick as we can. So important to note, though, even for the I2 instances, even for the instances like Hi14XL, you are interacting with a physical device. Now you're back to the back of the box, where you have actual behaviors of real physical services. And so, as is common with physical devices, there is variability in their performance. Right? So if standard EBS has crazy variability because it was built on best effort, provisioned IOPS is like a ruler. It's unbelievable the difference in your CloudWatch charts. Typical orders of magnitude, you're at 0.1% variability over weeks and weeks and weeks of behavior. This is at 1,010 and then 1,011 and 1,009. That's normal. Now the SSDs they're really fast. I mean, they're catastrophically fast. There's no getting around it. But they have variability. I mean, that's approaching 10% from 65,000 IOPS down to 61,000 IOPS for this test. That's multiple dozens of megabytes a second in difference. There's a 52,000 on that list. So be sure as you're testing your workload, recognize that when you use the instances with local ephemeral disk, that you're talking about the actual behavior of a physical thing there, and provision IOPS will tend to be significantly more consistent than that since it is a managed service, for lack of a better word. So performance, schmeformance, who cares? I have to buy this stuff with dollars and cents. What's the right choices to make in terms of when are the inflection points around one device versus the other? So what we've noticed is that there's one set of decisions that happen if you're thinking about this on demand. If you have a workload that's short term, if you have a workload that has an unpredictable term, it's pretty conservative to plan around provisioned IOPS in most cases. But as you go to much longer term, because of the value of reserved instances, where there isn't today a reservation model around EBS, drives down the cost of local storage because it drives down the cost of local instances. And as a result, long-term workloads may make more sense as you get efficient and optimized and you have better visibility into your workload to run on these kinds of ephemeral services. So another model, right now, because the high 1.4x large instances are so large, if you're smaller than this, provision IOPS is always going to be nice because you can dial it to exactly the speed that you want at those smaller sizes. But if you're very, very big, then high 1 is going to make a lot of sense. Now, what's happened, if you think about it, is I2, because of the I2 large instance, is a much smaller building block. So some of this guidance will shift, and high five for that. What that will do is also change the threshold at which provision IOPS makes sense if your systems can take advantage of that higher IOP throughput. Same kinds of calculus for the comparison between the storage instances, HS1 8x large versus the CC2 8XLs. In many cases, that choice is a little more complex. It is much more bounded by how long you're going to run the instance. And it's also important to note that for both of these models, we're not comparing against a single instance, because if you're using storage on a local instance and you have one copy, I will smack you. Don't do it. So you have to have two. You have to have replication of some kind. And so when comparing the two instances that you'd need, also remember the management overhead that. There's two computers to patch. There's two computers to check metrics on. There's two computers to back up. Maybe you do only one backup. OK, I'll mess with you. So costs for those two are also important to analyze. And as we add new instance types, as we change prices, that calculus will shift. There's also stuff that you can do at the software layer that has, in some cases, pretty significant impact on performance storage. We really do strongly recommend EXT4 or XFS. There are a couple different behaviors there. Also important to note that journal access alters the behavior patterns for most storage, so worthwhile experimenting there with the configuration of journal. Many applications don't make use of some costly file system features, particularly like no A time and no jury time. And setting read aheads low on provision IOPS storage. If you imagine that if you read ahead 512K for every read, and you only actually need this 4K read, you just spent, I think it's 32 separate IOs that you didn't need to spend against storage. Your storage will go very slow. Also, you may be able to note from this slide that I have a penchant for snapshots. I suggest that you poke that button as frequently as you even remotely think is reasonable, and then right after that, poke it again. So the EBS storage model is designed around the concept that each EBS volume holds at any given time less than 20 gigabytes of data that hasn't been snapshotted. So there's this weird thought that the more often you snapshot, the less often you'll need them, which is also something to sort of take into mind as you're planning. So we went from 1,000 to roughly 100,000. When I started as a solutions architect 3.5 years ago, 1,000 IOPS, it was rocket science. We worked really hard with customers to design and configure and optimize those implementations. You had a lot of work to do to get to that level, and we're roughly 2 orders of magnitude faster than that today. So you may also, as you've been looking through, evaluate the workloads that maybe you evaluated before. Even if you tested when we put provisioned IOPS out at 1,000 IOPS, it's 4 times faster now. That's a big difference for most workloads. My compute is not 4 times faster. My memory is not 4 times faster. All of a sudden, my storage is 4 times faster. That's a big difference. So as you're looking through workloads that maybe were impossible, you could never run that stuff in cloud, we're seeing people really finding no upper barrier. There isn't anything that you can't run in here. And we're excited about taking those big enterprise workloads on across the full range of different storage workloads. Your data warehouses, we're good with those. Your file systems, yep, we can do that. Your media storage, yep, we got that under control. Relational databases, check. So we have a lot of data here. This is the second time we presented it, so double feedback would be cool.